Let's start with two simple examples. So let's label this as example 0. And say we have y equals x, which we know quite well. It is this kind of graph. And let's put some inputs and outputs on a table. So let's start with -1, 0, 1, and 2. Those are the inputs, the x values, and the corresponding y values, of course, will be -1, 0, 1, 2. And you may be thinking, well, that's not a big deal. That's example A or 0A, and then now we're going to do 0B. A simple thing we're going to do is add 1 to the x, x plus 1. Um, and let's look at the table. This is what is important about this pair of examples. So -1 plus 1 is going to give us 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. So notice how the outputs got shifted, even though the inputs, so look at the inputs. The inputs go from -1 to 2, -1 to 2, one by one. The outputs got shifted to the left. Notice that. So the 0 is here, now it is on the left. The 1 is here, now it's on the left. The 2 is there, now it's on the left, 1 unit to the left. Had we put x plus 2, see, y equals x plus 2, whoops, plus 2, we would have -1, 0, 1, 2, the same inputs. But when we add 2 to each one of those, now we're at 1, 2, 3, 4, which is another shift to the left by 1. So the one thing we want to remember from this is that every time we add a quantity, we're shifting to the left, to the x. When we add a quantity to the x, we're shifting to the left, which is counterintuitive, um, because we may be thinking, hey, we're adding, so usually adding means to the right. But in this case, when we're talking about the output of a function, we're really reducing it or shifting to the left. So be aware of that. So the conclusion of these three examples, well, this is the baseline. And then by doing this, we notice that we're shifting to the left. And indeed, the graph actually has been moved to the left. So this would be y equals x, y equals x plus 1 would be to the left, and so forth. So every time we are subtracting a positive number, we are shifting to the left. Um, this is more dramatic when we have more complicated examples. So let's look at, whoa, I don't know why I put 2. This is example 1. Um, let's look at y equals x squared. And let's make sure we understand this graph. So most of us do already or are familiar, but it doesn't hurt to see it again. So we got 0, 0, 1, 1, and then 2, 4 is about here. And then we have 3, 9, which is outside of this page. So we have a nice parabola like so. Become familiar with points that belong to this parabola with whole numbers, such as, of course, 0, 0. That point, by the way, is called the vertex. And then we have 1, 1. And then up here we have 4, rather 2, 4. Yep. I was just double checking. Yep. It wouldn't make sense to have 4, 2. There. So that is 2, 4. And then on the left, we have -1, 1. And at the same level as the other one, we got -2, 4, same output. And then this goes up. All right. The reason why I'm bringing that up is because we are going to do transformations such as equals x, let's say plus 3. So we added 3 to the x. It is the same kind of equation in the sense that we have a variable squared, but now the variable is x plus 3. Now remember what happens when we add a number. We start shifting to the left. And the bigger the number, the more we shift to the left. So this parabola will be the same as is, but 3 units to the left. We don't have to necessarily draw every point, because if we didn't know how to even start drawing this, you could, just plot some random numbers and then start trying to catch some kind of behavior or some kind of pattern. But there is no need to do that if we understand how the plus 3 on the x changes this original graph. So we have to become familiar with this graph, and then we have to become familiar with transformations. This is one of the 10 transformations we're going to see in this video. So we have 1, 2, 3 units to the left, and then we have the same parabola. So copy this parabola down here. All right. So the vertex has moved from 0, 0 now to 0, 3. Rather, negative 3, 0. 1, 1. So again, that is because this x value has shifted 3 units to the left, giving us negative 3. The y value does not change, by the way, only the x value. This 1 moves to the left, and it gets to negative 2. So now we will be at negative 2, 1. This 2 moves to negative 1. Negative 1, 4. Notice that the 4 and the 2 and the 1 rather remain there. So everything moves to the left exactly by 3 units. So this point over here would be negative 4, 1, because that is 3 units to the left. And this point up here will be negative 3 units left of negative 2 would be negative 5. And then the 4 stays. Okay, so if we add anything to a function, we're going to be shifting the function. No, I said that wrong. If we add x, rather, a positive number to the x in the function, to the x, then we're going to be shifting to the left. On the other hand, if we add a number to the function, not to the x, so there's a difference, and this can be confusing. So let me right away clear this up. There's a difference between adding 3 to the x, 3 to the x, versus adding 3 to x squared. Those two are very, very completely 100% different. In the following sense, this actually adds 3 to the previous output, to this output, the normal output, or the starting output. There's no such thing as normal, I suppose. It's just the starting, where we start. So if we start with this output and we add 3 to the output, then the whole output is shifted. So this represents a shift to the left, shift to the left by 3 units. And this, on the other hand, represents a shift up by 3 units. That is also called a vertical shift. So we have a shift to the left and a shift up. And it is very, very important to distinguish one from the other. I can easily see problems in multiple choice questions, and even in not some multiple choice questions, where I can ask, hey, which one is this? Is this up or to the left, or down or to the right, just to give more choices? Well, we have to understand this is up, and we have to understand this is left by 3 units. Now, let's convince, I mean, I'm telling you, and you're probably believing, which is which is good, but I always ask my students to be what I think is skeptical, a little skeptical, not very skeptical, but a little skeptical, in the sense that yes, I believe you, but let me double check. Um, yeah, yeah. I think any student in any class in any school should always be a little skeptical, in the sense that yeah, I believe you, but let me double check, let me try, let me see, let me look at some examples, let me verify. We expect students to do that. Um, if for no other reason, because we make a lot of mistakes. Teachers do make mistakes. Let's look at this equation, at this function versus this one. So we're going to look at two functions. And so this is the starting one, and this is the transformed one. So if we have y equals x squared, the table corresponding to that will be, and I'm just going to plot some numbers. So 0, 1, 2, -1, -2, and the outputs are going to be 0, 1, 4, 1, 4. They are nicely symmetric from the 0. By the way, just since I was talking about symmetry, those outputs are going to be symmetric around -3, not around 0. But this one is around 0. Okay, so just keep that in mind. And now let's look at y equals x squared plus 3. I guess order of operations is important here. That means that square first, and then we're going to add 3. And we already squared here. We're going to put the same inputs, -2, -1, 0, 1, 2. So square the 0 and add 3, we're going to get 3. Square the 1 is 1, and 3 is 4. Square the 2, 4, and 3, 7. Square -1, which is 1, and 3 is 4. Square -2, 4, and 3, 7 again. So again, we have symmetry around the 0 because we got 3 in the center, and then the 4 on each side, and then the 7 on each side. Yes, so we have the same center symmetry at 0. That's where the symmetry happens, but the outputs have gone up by 3. So 0, 3, 1 and 3, 4, 4 and 3, 7, 1 and 3, 4 again, 4 and 3, 7. So the whole thing has moved up. Now, that is confusing initially when we haven't developed an intuition about this. Adding 3 shifts to the left if we add 3 to the x. Adding 3 to the whole function moves up. So 3, oh, so 3, and we're just going to continue. Let's just sketch the graph. So 0, 3, and then we have a parabola. That parabola should be more symmetric. My picture is not very symmetric. And then we have 1, 4. Up here somewhere we have 2, 7. And because we have symmetry around 0, we have -1, 4, and then -2, 7. The normal standard or initial output of -2 when we are looking at x squared, oh, I didn't write down the y equals x squared plus 3. The standard output for x squared and -2 would be 4, but then we add 3, and that's how we get 7. Make sure you know your transformations. They are very important. And there are 10 different transformations. So we've seen 2, and there are 10. So shift to the left, add a number. Shift up, add a number, but outside. Before I continue, let me go back to example 0. Back to example 0. Yeah. where we had y equals x plus 1. This can actually be seen in light of what we just saw in two different ways. Somebody could say, well, we're adding 1 to x, so we're shifting to the left. Yeah, but somebody else could say, wait a minute, we're adding 1 to x, so we're shifting up. So which one is it? Actually, it's both. We depending on how we think of this. So if we think as, I'm going to emphasize x plus 1, starting with x, so that is a shift to the left. So y equals x is a 45-degree angle line that goes through 0, 0. This guy is, yes, a shift to the left by 1 unit. So now we are looking at this kind of picture. So move to the left, and there we have it. I'm just going to do it with my ruler. Yep, move to the left, to the left. So push this way, and then we're in this picture. Okay, but we will have the same effect if we push up. Now, that is not true for all functions. And it isn't true either for functions that are a, no, I take it back. It is not true for all functions that we have exactly the same kind of push in different directions. However, it is true that we may see transformations in more than one way, but the transformations are going to be different by different measurements, by different quantities. We're going to get to that later as we see more and more examples. All right. So how many transformations did I say there are? There are, or we're going to study 10 different transformations. And we have seen 2 of them. If we add a positive number, x plus, I'm going to put an actual number, plus 1. But then you understand, I hope we understand that if we add x, rather 7, for instance, then we're going to be shifting to the left by 7 units. Or if we put a 3, we're shifting to the left by 3 units. So adding, let me back up a little more. Whenever we transform, we have 2 things. We have old and new. So let me scratch that and start a little bit over, not too far back though. Whenever we have a transformation going on, we have old, and then we have a transformation happening, and then we have something new. Okay, that is the whole point of a transformation. You start with something old or different or standard or whatever you want to call it, initial, and then we transform and we end up with something different. That's what the whole point of the word transformation. All right. So, and when we have functions, if we have the same name for the old and the new, that could be confusing. So the old one, for purposes of this video, is going to be f of x. And the new one is going to be y. So that is the way I'm going to distinguish the two. Y is going to be new, and f of x is going to be old. That is completely arbitrary. I'm doing that so we understand which one is the old one and which one the new one is. Okay, so now let's go back to the shift to the left. Okay, so if we have a new function that's new, made up by an old function, that's the old function, in which we add a number, and I'm going to change the 1. I had 1 before. I'm going to change it to a 3 just because. So if we add any positive number, this new function is the old function shifted to the left by 3 units. So this represents a shift to the left by 3 units. Okay, versus adding 3 after the function is performed. So there's a big difference. Mathematics is full of nuances like that, and that is the whole point of learning mathematics, so that we can actually tell the difference. Oh, the three is inside versus the three outside. Yeah, we have to be able to visualize that. So for instance, in those examples 2 and 3, here the 3 is inside of the x squared, while here the 3 is outside of the x squared. And that makes a big difference. On one hand, we have a shift to the left. On the other hand, we have a shift upward. So in this case, we have a shift up, simply up, by 3 units. Okay. Well, it doesn't take too much to extrapolate, to infer that if we subtract 3, then we're going to be shifting in the other direction as if we were adding 3. And that is exactly what is going on. So that is a shift to the right by 3 units, the units of the x axis. Well, and again, if we subtract 3 outside of the function, after the function has already been performed, then we're shifting down by 3 units. So this represents a shift down or downward by 3 units. Now, mind, this is a little confusing because, I mean, -3 going down, that makes sense. +3 going up, that makes sense to me. Those two make sense. The other two, the horizontal changes, are counterintuitive, in my opinion, because subtracting 3, in my mind, I'm thinking, oh, that's to the left. No, 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 no. We have to fight that and say, no, no. That means we're going to shift to the right. And adding 3 means shifting to the left because the outputs have to catch up in order to end up with the, let's look at this 0th example when we had a table. Remember, when we added 1, the 0 starts here, because because the inputs have to go farther to the left to catch up with this 1. That's what's going on. So yeah, those are 4. How many to go? 6, because there are 10 total transformations. So there's 4 here, represented here, and there are 10 to go, rather 6 to go. There are 10 total. So let's say 6 to go. 6 more transformations to go. Okay. We could, let's look at the rotations. They're not rotations. There's a better name for that. Let's start with y equals negative f of x. It's a reflection. Yeah. So this is a reflection over the x-axis. So putting a negative in front of a function reflects over the x-axis. So this is a reflection over x-axis. We're going to do a couple of examples of that. And but y equals f of negative x, on the other hand, and those are, for the most part, different. Occasionally, they're the same. But in general, they are different. That is a reflection over y-axis. Okay. So example 4. It looks like 1, 2, 3. Yep, 4. Okay. So let's say you have y equals the opposite of the absolute value of x. That's an important example. Okay. As we do this, let's first think of just the absolute value of x. Okay. This is not, they're not the same. I'm just starting out with this because this is a transformation of that. That's why I would like to refresh my memory as of what this looks like. This, as we know, is, and if we didn't know, now we know it, is a V function, a V-shaped function. It is a 45-degree on one side and 45-degree on the other side relative to the horizontal. And it keeps going on like that forever and ever and ever. So that is the regular absolute value of x. We saw this in a video. What the absolute value does, it folds the function over the x-axis, and so everything is on above the x-axis, and that's great. This, as we have noted here, is a reflection over the x-axis, a total reflection. So if we start with this, so this is this function, this guy will be the other way. It flips over, it reflects over the x-axis. So now the graph is going to look this way. That's it. As simple as that. That's all we have to do, just reflect over. Yep. Example 5. Y equals, if we put the absolute value and the negative inside the x, then we're going to be reflecting over the y-axis. But the graph is symmetric already on the y-axis, around the y-axis. So when we rotate, we still end up with the same picture. Yeah. Only when a picture is not symmetric over the axis in which we are reflecting, then we get something different. So here we got something different, but here we got the same picture. Yeah. It's like if I show you the back of this page. Oh, that's a bad example. A blank one. If I show you a blank one and then we turn it over the center, well, you end up with the same picture, the same page. It's just the same thing. If you just flip it over, it's the same thing because there's nothing written on it. And that's kind of what's going on here. If we take this V and we reflect it over the middle, we're going to end up with the same picture. Nothing changes. However, this V reflected over the x-axis, well, there was nothing on the other side. So by the time we turn this over, now there's going to be something underneath and nothing above. Yeah. Yep. So those are two transformations that are going on. Two more, and in addition to the 4 more that we had. Those 6 that we had so far, shift up, shift down, shift to the right, shift to the left, reflection over the x-axis, reflection over the y-axis, those are actually the easy ones. There's going to be the next 4, in my personal opinion, are more difficult. But before we go into those 2, I just thought of another example that we should know really well. Let's review this function. So this is a new a refresher. Square root of x. What does that look like? I like this one because this is not symmetric. It's a good example to do. This is a half a parabola opening this way. Starts at 0, 0. It goes through 1, 1. It also goes through 4, 2. Eventually goes through 9, 3, and so forth. Okay, let's look at an example 6 based on this one. Yeah, this is a good example to show. Y equals negative square root of x. Now, this assumes we are familiar with that picture. And this also assumes that we know what a negative in front of the function does. It reflects over the x-axis. Please memorize that, remember that. Um, so that means that the picture corresponding to this will be that. See how fast it is? If you know your basic functions, and if you know your transformations, what the transformations do or how they act on a function, drawing the picture is very, very fast, very, very quick. Yeah. The details can be filled in after you um, reflect or shift. This point is still going to be 0, 0 because it doesn't do anything after we reflect. And then we have 1, -1, 4, -2, and so forth. Another example, what about negative? Oh, that's what we just did. What about the negative being inside of the root? Let's see if I can fix this. There. So instead of having the negative outside of the root, we're making the x itself negative or opposite. Okay, that is a different picture. That gives us a different picture. Not down, but, whoa, that's wrong also. Never mind that. Because we are starting with this one. I was reflecting over the y-axis this one, but that's not the one I want to reflect. I want to reflect the original one. Whoa. Actually, I'm going to erase the arrow, and we're going to make an example of that in a moment. So if we have the original one and we reflect over the y-axis, which is what that negative does, what we have is this picture instead. So that's the one that corresponds to this. It turns out that there is a function that has this picture. Let's make an example out of that. Okay, so this picture comes from the original picture by first reflecting over the x-axis and then reflecting over the y-axis. So what is the function that goes with it? It would be opposite of the square root of the opposite of x. That's a reflection over the x-axis, and that represents a reflection over the y-axis. Yep, yep. So we have to know a few things. We have to know our basic functions, such that the absolute value, how it looks like, or the x squared, or the square root of x. So we have to know some basic functions. Let's make a list of the basic functions we have to know really well. So basic functions to know well. Well, f of x equals x, which is just this. F of x equals x squared, which is a parabola opening up. F of x equals square root of x, which is half a parabola opening to the right. F of x equals x cubed is a good one to know. It is an S curve, sort of S. It's not really an S. I call it an S curve, but it's not really S because that's not how we draw the S. Even if we rotate it, that's like an S, turned over. But it still sort of is an S curve. What I mean by that is that it curves one way up to the origin, and then it curves the other way after the origin, and it goes upward and to the right as we go in this direction, and downward and to the left as we go on the opposite direction. Oh yeah, the absolute value of x, which is that, and 1 over x, very, very important. 1 over x has two asymptotes, one asymptote this way and one asymptote this way. As we move on into college algebra, you're going to see other functions. Basically, logarithms, um, exponential functions, and more rational functions. Um, yeah, logarithms and exponential functions we have to know really, really well. Um, but those are the basic ones. Most of the examples we're going to give are going to be, especially in this video, are based on those examples: absolute value, cubic, square root, x squared, just x by itself. Oh, there's one more I almost forgot. F of x equals the cubic root of x, which that one does look more like an S curve, and it keeps going down and down this way and up that way as we move to the right. So that does look more like an S, a stretched S. This one is kind of like an inverted S. Those two are related, the cubic root versus x cubed. The same way as those two are related, square root, because that is half a parabola, this is a full parabola. Those two are related because if you fold half the bottom half over, you get this one. So those two are related. This one is it's pretty much on its own. Uh, it does have a vertical asymptote and a horizontal asymptote. So those are your basic functions you really, really need to know as a student. 1, 2, 3, 4, 5, 6, 7. Okay, so we got 7. If I think of another one, I'll let you know. We'll add to our arsenal of functions to know. And so far we have seen 4 shifts as far as transformation. So now let's talk about transformations. And we have seen 4: a shift to the right, a shift to the left, a shift up, a shift down, a reflection over the x-axis, so over the x-axis, a reflection over the y-axis, so that's 6, 1, 2, 3, 4, 5, 6. And now we got 2 more, which are 2 stretches and 2 shrinks. Before we start with those 2, let me define what I mean by a large number versus a small number. So large or big number versus small number. And if you're thinking, well, that doesn't make sense because large and small are relative. They're completely relative. And I agree. Uh, we cannot really talk about large and small in general because those are relative terms. But I want to standardize them in mathematics. So a small number for us will be a number between 0 and 1. So I'm going to provide a small definition or a little definition. So yeah, a small number is a number strictly between 0 and 1. Now, strictly means not 0, not 1. It has to be in between. Can it be 0.99? Sure. Can it be 0.999? Yeah. Can it be 0.109s? Yeah. Can it be 0.00001? Sure. That's a small number. They're both small. So if we're between 0 and 1, we got a small number. What is a big number? So this is my definition of small and big. I don't think it is universally known. That's just my own personal definition. So a big number is a, you know what? I should have said real because although it is understood that if it is between 0 and 1, we're talking about real numbers, a small, but let's add that to this, real number, just to be sure. a big real number is a number that is bigger than 1. That's it. So bigger than 1, big. Between 0 and 1, small. And that's it. Those are the only two. What about 1? Well, 1 is in the boundary. So 1 is not big nor small. It's just 1. It's in the middle. It's between small and big. And 0 is not a small number. It is the bottom end of smalls. Okay. So that is a big nuance in mathematics. The numbers that are small don't behave quite the same as the numbers that are big. Let me give you an example. What is the square root of 9? So 9 versus its square root. Square root of 9, which is 3, by the way. Well, this number is bigger than that. So it is true, you know, square root of 16. If you compare 16 with its square root, you get 16 and 4, and that number is bigger before we take the square root. So we may be thinking, oh, so that's always the case. But no, that is not always the case. Because what is the square root of 1 over 9, the reciprocal? Well, the square root of 1 over 9 is square root, well, of 1 over 9, which is the square root of 1 over the square root of 9, which is 1/3. Now, which one is bigger? The 1/3 is bigger. I mean, think about a pie and split it up into 3 slices. Well, you get a big slice. 1/9, if you take the same pie and split it up into 9 pieces, you get a thinner slice. So this guy is way bigger. Versus this, in this example, this one is the bigger one. See, so now the main reason why that is happening is because this is a small number, while this is a big number. This is bigger than 1. This is smaller than 1. So small numbers and big numbers don't quite behave the same way all the time. Yeah. So that's why I'm differentiating them. Now let's go back to transformations. This is going to be relevant when we are talking about transformations. Yeah. So how many transformations do we have this far? We got 6. Shift to the right, shift down, shift up, shift down, reflecting over the x-axis, reflecting over the y-axis. So that's 6, and we got 4 more to go. Let's think about a vertical stretch by a factor of 3. So a vertical stretch by factor of 3. Make sure you put down factor, please, when you are describing this stretch. Means that the graph gets stretched away from the x-axis. Boy. So what does that mean? That means that the graph is stretched by times 3. So whatever is 2 units, now it's going to be 6 units tall. But there's another important thing to say, away from the origin. No, not from the origin. Away from x-axis. Yeah. And the formula that we are going to see is this. The new function, which is a transform function, is 3 times the old function. So that is a stretch, a vertical stretch. Yeah. So as an example, which one do we want to do? Let's do this guy, the square root of x. And which example are we in? 9, because we did example 8. So example 9. Okay, so we're going to start with, see, whenever we're talking about transformations, it's going to be an old and a new. So this is the old one. Let's talk about f of x equals the square root of x, which we know well. It looks like this. So it is important in math not just to know something, but to know something well. That means that we got to be very, very familiar with them. 4, 2. Yeah. Yeah, it is good to get to know the math concepts well. Not just know them, but actually absorb them, digest them, making them part of us. Okay, so now we have a new function. Now, oftentimes, people are not going to tell you what the old one is. It is understood. But the new function, the one we want to sketch is this guy. Y equals, let's use the same as the example up here, or the idea that I was, square root of x. So if we multiply by 3, what that does is that it stretches the graph, making it taller by the same, while we are here. I mean, taller here. Eventually, this is what I'm trying to say. Eventually, this is going to get taller and taller and taller as we go to the right farther and farther. But it's going to get taller sooner. That's what I was trying to say. So the graph is going to get taller away from 0. So it's going to have this kind of curve instead. So we start with 0, 0, because the output of 0 gets multiplied by 3, giving us still 0. 1, 1 is not going to be at 1, 1 anymore. It is going to be at 1, 3, because the output gets multiplied by 3. 4, 2 will not be at 4, 2 anymore. It will be at 4, 6, because the 2 gets to be multiplied by 3. So this is what's going on. One of the things we're going to ask students to do is sometimes is to transform a function without an equation. Transforming without initial equation. Or the better way to say it is, or transforming graphs. Yeah, that's better. Transforming graphs. All right. So what do I mean by this? Let's say we have a graph. Let's make it simple. So f of x, I'm not going to give a formula for it or anything. I'm just going to give a picture. So pretend we start at 1, 2. And we draw half a circle. So it starts at 2, and we have half a circle. So 2, 3. And it stops here at 3, 2. So it starts at 1, 1, 2, goes up and down half a circle, and ends on 3, 2. It has to, well, because we're doing a semicircle that is leveled horizontally, that means that if we start at 2, we end at 2. And this highest point will be 2, 3. Boy, that is a little confusing. There's a lot of 2s and a lot of 3s. This is 3, 2. This is 2, 3. There is 1, 2. That's all right. Okay. Now we're going to stretch. So now the example is this. Multiply the function by 3, which means we're going to stretch vertically. Now, this is what I mean by, this example is going to show what I mean when I say away, we're going to stretch vertically away from the x-axis. So this guy, this semicircle becomes more of a half an oval, And it is going to be, instead of being 1 unit tall, so first, keep in mind this is 1 unit, 1 unit. So now it is going to be 3 units tall. But on top of that, the gap between the x-axis and the starting of the semicircle will be also multiplied by 3. So not only this guy gets stretched, but the gap between the x-axis and the beginning of the curve of the graph gets also to be stretched by 3, by a factor of 3. So to draw this picture, okay, we're going to start with, I need a lot more space, so hopefully this will do. So instead of starting at 1, 2, we're going to start at 1, 6. 1, yes, but then 1, 2, 3, 4, 5, 6. Much higher. That's where we start. This point up here, which is 2, 3, is going to be at 2, 9, because we're whoops, I meant to put an X here. Sorry about that. Not 3 and X. Okay. So this is going to be stretched by 3, the output, not the input. And so now we're going to be at 2, 9. That was 6, 7, 8, 9, 2. So about there. And then we come back down to 3, 6. 3, 1, 2, 3, 4, 5. There we go, 6. So we're going to have a stretched circle, which is not a circle anymore. It's going to be and half an oval. I wonder if it is an ellipse, half an ellipse. I'm going to guess yes, but I have to check. So I have to get back with you if you were asking if that's an ellipse. I have to think about how to verify that indeed we have an ellipse. Let me check very quickly here on the side. Let me pause. Yep, I just checked. It is an ellipse. So when we stretch a circle or semicircle vertically or horizontally, for that matter, either way, we end up with an ellipse. So this is half, I'm sorry, not an ellipse. Ellipse? Yeah, it is an ellipse. Ellipse. So this is an ellipse. Circle, ellipse, hyperbolus. Yeah, that's an ellipse. Anyway, so this is half an ellipse. This point is 2, 9. This is 1, 6, 3, 6. The point I wanted to make, though, is that not only this guy, not only the semicircle changes its shape, now it has a different shape. It went from circle to ellipse, or half of a circle to half of an ellipse. And the gap between the x-axis and where the figure or the graph starts also gets stretched. So watch out for that. That happens when we have a vertical stretch by a factor of 3. 3, mind, is a big number, so that's why the picture stretches. The width also is important. The width does not change. It is still 2 units across. Okay. A vertical shrink by a factor of, I'm going to use 1/3. 1/3 is achieved when we multiply a function by 1/3. Okay, so the graph shrinks down by 1/3 of what it was before. The other thing to notice, though, is the gaps also shrink by the same factor. Yeah, yeah. Um, so I'm going to elaborate on this. Um, not only the the graph becomes shorter, a third of what it was before, but the gaps um, to the x-axis get shorter, to x-axis, or in between x-axis and the graph, become shorter. Okay, let's look at this initial graph again. So pretend we have the same initial graph. I'm going to copy it down as an example. So 11, so pretend you have 1, 2, so 1, 2, 3, 1, 2. So that's where we start. 3, 3, 2. And then we go only up 1 unit. So we have a semicircle, a perfect, pretend that is a perfect semicircle. Okay, so the top of the point is 2, 3. This point here is 1, 2. That point is 3, 2. Okay, so we got a nice semicircle. Okay, what if we did y equals a third of f of x? So this picture is f of x. But now we're going to do a new one. So this is the starting point. Start with this f of x. And now we have a new one, a new function. And of course, I don't want to use the same f in both places because it wouldn't make sense. This is a new function, a different function made up by the old function, that one. And what we're going to do is shrink it by a third. So instead of this being 1 unit tall, now it will be 1/3 of a unit tall. So it's going to be more narrow. It is still going to be roundish, but more narrow. The width is going to be preserved. Not only that, the gap also gets to be reduced by a third, by a factor of a third. Did I put a factor? Yeah, factor of 1/3. So instead of starting out at 1, 2, now we're going to start up at 1, 2/3, because 2 times a third is 2/3. And we start out with 2. All right, so let's see. I'm going to make the units, I kind of want to make them a little bigger, but at the same time, I don't want to make them bigger so we can tell the difference. So these are the units, 1, 1, 2, 3. So we're going to start at 1 and 3 because that's as far as this stretches. Oh, and just as a quick review, what is the domain and range of that? We saw that in a previous video. The domain goes from 1 to 3. And the range goes from 2 to 3. Okay, just a quick review of what we did before. Anyway, so the gap is 2 units tall. The gap reduces to 2/3, which is about here. Whoa, it's really tiny. And so that is the starting point, as opposed to there. It gets down below 1. 2/3 is below 1. Not only that, now the graph, instead of being 1 unit tall, it is 1/3 tall. So remember, this point is at 2/3 up. Well, now we're going to increase this just by 1/3. So it's going to be very, very, it's not flat, but it's getting more flat than it was. It wasn't flat, actually, but now it's kind of flattish. So this point will be 2, 1. Because, and that is easy to figure. 3 multiplied with 1/3 gives you 1. That's how we get the 1. This point, the ending point, will be 3. So we're preserving the input, but the output gets to be multiplied by a third. And 2 times a third is 2/3. This guy, on the other hand, well, likewise, rather, not on the other hand, gets also is also shrinking by 1/3. So now we got 1 comma 2/3. Note that the input does not change. The input is the same. The inputs don't change. The domain, in fact, is the same. The domain goes from 1 to 3. The range has changed dramatically. It goes from 2/3 to 1. That's a comma, to 1. Oh yeah, this is not easy. And now it's gonna get worse. I saved the worst for last. In my opinion, you may be thinking, hey, that wasn't so bad for the next example I'm gonna show you, but in my opinion, this is the worst. Okay. So we have 8 so far. Okay, a shift to the right, a shift to the left, a shift up, a shift down, a reflection over the x-axis, a reflection over the y-axis. And remember how we did this. This is by adding, no, see, I'm getting already confused. This is by subtracting a number to the x. This is by adding a number to the x. This is adding a number to the function, subtracting a number to the function, putting a negative in front of the function, putting a negative in front of the x. See, that's already a little confusing. And then we have a vertical stretch and a vertical shrink. So stretch, shrink, stretch, shrink. And the way we achieve this is by multiplying the function by a big number, and this is obtained by multiplying a function by a small number, which makes sense. Big number, small number. So the only two left to do is a stretch horizontally and a shrink horizontally. And then we have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I haven't told you how to do this. And this is the weirdest one too. Well, the two of those are kind of weird. And I'm going to show you how. To horizontally stretch a graph, by a factor of a, let me put a number, by a factor of 3, comma, we multiply the input by 1/3. Isn't that, I think this is wild. In other words, if you want to end up with a new function in which the old function gets stretched by a factor of 3, what we have to do is do 1/3 x. And to me, that is a little bizarre because that is sort of the opposite. This is a small number. Multiplying the input by a small number produces a stretch by the reciprocal. Those two are reciprocals of one another. In other words, you do 1 over this and you get that. 1 over that gives you that. And by the way, I missed to tell you that the reciprocal of a big number is a small number. The reciprocal of a small number is a big number. So they flip-flop. So this is actually a horizontal stretch, which is anti-intuitive because we have a small number. I don't know about you, but that blows my mind a little bit because it's completely anti-intuitive. However, if we think about it if we put it in perspective, that is kind of what happened when we were shifting to the left. We were adding a number which is anti-intuitive. And that is in fact true for all the horizontal changes. Whatever we do is sort of the opposite of what we expect things to happen. With vertical changes, there's, we have the normal thing. Add a number, you shift up. Well, by that I mean add a positive number and we shift up. Subtract a positive number, we shift down on the function. But if we add a positive number on the x, then we're shifting to the left. If we subtract a positive number on the x, then we're shifting to the right. Okay, if we multiply the function by a big number, we're stretching vertically. But if we multiply, and if we multiply the function by a small number, we're shrinking. That makes sense. What doesn't seem to make sense at first is that if we multiply by a small number, then we are stretching horizontally. Let me show you what happens. Example 12. In fact, let's do this on a new page. Example 12. Start with, we're gonna, since we are used to our graph, let's stay with that graph. 1, 2, 3, 1, 2, 3, starts at 1, 2, ends on 3, 2, goes up to, it's a semicircle. Okay, that point. And then, okay, so that is, what is the actual formula for this? I haven't told you, but that's the point. I don't want to tell you either. We want to work more abstractly with a picture and see how the transformation affects the picture. Okay, so this is f of x, the same one that we've done in a couple, in the last couple of examples. So the example here is y equals f of 1/3, whoops, 1/3, I closed the parenthesis too soon, 1/3 of x. There, okay. So remember, that's a small number, but it's inside of it is multiplying the input, which means we're actually stretching by a factor of 3. So this is a horizontal stretch by a factor of 3. Now remember, the gaps between the axis and the starting of the function also get stretched by a factor of 3. So this gets wider. Right now, it's 2 units wide. We're gonna, so let me write down what's going on. So we're gonna stretch horizontally by factor of 3. I can see asking in a test, hey, what is the factor we're stretching by? And if you put 1/3, that wouldn't be correct. We're stretching by 3. And how do you know that? It's the reciprocal. It's 1 over 1/3, which is 3. Or just flip the fraction upside down, and that's the same effect as having a reciprocal. Okay, so now the graph, I don't need to make it tall. I just need to make it wide, because now we're going to stretch horizontally. So this gap, right now there's a gap of 1 between the y-axis and the beginning of the graph. That's going to be stretched by 3. So the beginning of the graph is going to be 1, 2, 3. 1, 2. We're going to start at the same level, but here's where we're going to start. The end of the graph is at 3, but we're stretching by a factor of 3. So we're going to end at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to stop here. Isn't that wild? The height does not change, though. We're still at 2. And the top is also going to be at 2, rather 1 unit above that. So the top is going to be just there, in the middle between 3 and 9. Let's count. 1, inward, 2, 3. So this is the middle, which we know will be 3, 4, 5, 6, which makes sense. 3 to the right of the 3 and 3 to the left of the 9. That puts us at 6. So this coordinate will be, or this point is going to have 6 comma and 3. The 3 does not change. Let's recall this is 2, 3. This is 3, 2. This is 1, 2. So now the 1, 2 became 3, 2. The 3, 2 becomes 9, 2. The 6, rather the 2, 3 becomes 6, 3. And the graph is this. If we were doing a full circle, then it would be an oval like that. So what we did is we took this guy, stretched it. Along with that, we also shifted because we also have to stretch the gap. So not only the graph gets stretched, but the gaps also get stretched by the same factor. Whoa, isn't that wild? Yeah. Wow. I think this is really, really cool. Okay, so we have a stretch. How about a shrink? So the way we get a shrink, a horizontal shrink, because when we are talking about stretch and shrink, we have to be more specific. Do we mean vertically or horizontally? Because that makes a difference. By the way, the domain here, just to recall, domain of the original graph is from 1 to 3. The range is from 2 to 3. Of course, here the domain has changed, not the range. The domain goes from 3 to 9. The range doesn't change from 2 to 3. Okay. How about a horizontal shrink? Let's go back to this page. Okay. So 2 horizontally shrink a graph by a factor of, say, 1/3. We multiply input by not 1/3, by 3, which is sort of backwards, but that's the way it is. F of 3x. That changes the graph horizontally, but it shrinks it. By the way, those two are very important in electricity and in physics, because the sine function, which is a wave, the cycle gets shrunk or stretched, and that's exactly how it is done with multiplying the input by a big number. So if we multiply by a big number, then the cycles get way shorter. If we multiply by a small number, then the cycles get bigger. So there is a lot of applications of this. This is widely understood and known and used in physics and electricity and probably many other places that I don't know about. So let's do an example. Let's start again with our same, start with 1, 2, 3, 1, 2, 3. So 1, 2, and 3, 2 go up to 1. So there's a semicircle. Pretend that is a semicircle, a perfect semicircle, half a circle. And we want to do things such as, so this is f of x, and we want to have a new function made up with this guy that is going to be f of 3x. That's going to be quite a reduction. We're going to shrink this. Mind, when we shrink when we shrink or stretch, we're in addition of shrinking the graph, the gaps between the graph and the axis also gets shrunk. Um, so right now we have a gap here, and you may be thinking, hey, wait a minute, this is, are we going to shrink this gap or that gap? That's part of what you have to learn. Yes, it is. Yes, absolutely. Yeah, that's part of the question. Which way are we going to shrink? Well, look at this. This is anything that happens inside of the x or with the x is horizontal. Anything that happens outside of the function is vertical. We're going to do a little table in a moment about that. But let's finish this one up, this example. So this gap is a nice gap of 1. That gap is going to be shrunk by a third. Oh, by the way we describe this is we have a shrink. Oh, I did describe it. Let me just make sure I did describe it in here. So we have a shrink of a graph by a factor of 1/3. I can see asking this question on a test and asking what is the factor by which this graph is being shrunk. And if you put 3, that's going to be wrong. It's got to be a third. So remember that, please. All right. So the gap is reduced by a third. So instead of starting at 1, 2, we're going to start at a third, 2. Boy, again, I hesitate to use the same units because things are going to be very tiny, but I'm going to stick with the units. So the gap of 1, the pen kind of is in between. Now it's going to be reduced by a third. So we still start at 2, but much sooner. So the gap is tiny. You can hardly see it. And this is 3 divided by 3 or multiplied by 1/3 gives us 1. So the whole semicircle, which is not a semicircle anymore, starts there and ends there. And it's only 2/3 of a unit wide. However, the height doesn't change. So it still goes up to 1, well, and ends in the same spot on here. So this point, which used to be, the point here used to be 2, 3, now is 2/3, 3. This point, which used to be 3, 2, now is 1, 2. And this point on the left, which used to be 1, 2, is 1/3, 2. What happens is that the inputs get transformed, not the outputs. And you may be thinking, oh, wait a minute, this is confusing. Which one is which? Let's make a table of that. Okay. So we have 10 transformations. I'm going back. Here they are. Okay, we got shift to the right, shift to the left, shift up, shift down, reflection over the x-axis, reflection over the y-axis, vertical stretch, vertical shrink, horizontal stretch, horizontal shrink. So those are 10 different ones. Let's classify them into horizontal and vertical. So let's split into 2, vertical versus horizontal. Okay, so vertical means shift up, shift down. Vertical stretch, vertical shrink, and reflection over the x-axis. Horizontal, shift to the right, shift to the left, horizontal stretch, horizontal shrink, reflection over the y-axis. Okay. So to shift up, take the function and add, I'm going to stick with 3, a number. Shift down, subtract 3. Stretch, multiply by 3. Shrink, multiply by 1/3. Reflect over the x-axis, put a negative in front of the whole function. What is the difference here? Shift to the right, and we gotta subtract 3 from the input, not the function, but the input. Big, gigantic difference. Shift to the left, add to the input. Horizontal stretch, multiply by a small number, such as 1/3. Of course, if this was 1/2, we're gonna stretch it by twice as much, instead of 3 times as much. Shrink, multiply the input by a big number. That's why I was making a big deal about big versus small number. And reflection over the y-axis, put a negative in front of the input, not in front of the function. Sometimes, occasionally, it won't matter which way we do it, but most of the time it does matter. And then the next question to ask is, okay, all of these vertical changes change the y. So this is y values are changed. When we do horizontal stuff, x values are changed. And there's going to be examples where we're going to have both of them. One thing that I haven't seen in books myself, but I don't see too many books, so that doesn't mean it isn't there, is a transformation of a very, 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 very tiny simple function with only one point in it. So let's talk about that, because I'm very likely going to ask that kind of question. Transforming one point. Transforming one point. That's it. The smallest function you can have is with one point in it. Otherwise, you have no function. So 1 point is the smallest function you can have. Let's do a few examples. Example 14. Okay, assume, and I'm just going to make this up, 10, 20 belongs to f of x. Okay, let's do a whole bunch of problems. So the generic question for all of these problems is as follows. What point belongs to A? Okay, so y, so that's a new function made up by this old function. The old function has 1 point in it. Okay, so let's say you have f of x plus 5, question mark. So the question is, what point belongs to this function? Okay, so we have to start thinking, oh, we're adding 5 to an old function, so this is a shift. Is it to the left or up? Well, it's happening outside of the function, so that means up. So instead of 10, 20, the answer to that would be 10, 25. We go up by 5 units. And I can see students getting confused with this other question, x plus 5. Whoa, that means a shift to the left. So if we start out at 10 and we move 5 to the left, we're going to be at 5. But remember, we're started out with 20. These are separate Yeah, we still have the same function, the same f, which has this point in it. So not 25, 20. Pretend that question, this question is independent of this question. Yeah, yeah. So there's the answer to that question. There's the answer to this question, and those two are independent of the next questions. So watch out, guys, because this is confusing. What about negative f of x? Question mark. You know, still we have the same question. What point belongs to y equals negative f of x? Okay, so that means we are reflecting over the x-axis, which means that the y is the one that changes. 10, negative 20. Not to be confused with, and I can see students getting really confused with this, f of negative x. That's a reflection over the y-axis. So the x is the one that changes. Instead of 10, 20, now we got negative 10, 20. Whoa. Okay, what else can we do? Well, the subtracting is similar. E, y equals 5 f of x. So that means a stretch, which a stretch because it is outside, by a factor of 5. A vertical stretch. Oh, the vertical stretch affects the 20. So now we got 10, 100. Not to be confused with f 5x. That represents a horizontal shrink by a factor of 1/5. Not 5, but 1/5. So now we're at 220. And then you can do a whole bunch of things. Gee, let's stop with this one. Let's say you got, man, and it can be, let's do more than those. How about f of x minus 6 plus 7? Question mark. So same question. What point belongs to y equals f of x minus 6, close the parenthesis, plus 7? So this represents a shift to the right. So we go from 10 to 16. That represents a shift up. So we go from 20 to 27. And it can be even more convoluted than that. H. So those answers, all of those problems are independent. So y equals, oh yeah, this is a good one. 5f of, let's just say 2x. That's an evil laugh. Of course, I'm joking. I'm not evil. I'm just pretending to be evil to make it funny. So here's the evil laugh. There we go. Okay. Boy, I better stop recording. I'm beginning to goof up too much here. Anyway, the vertical stretch changes the 20 into a 5, rather the 20 into 100. The horizontal shrink changes the 10 into a 5. What about, oh, I like this one. 2 f of x plus 7. Okay, so we're gonna stretch. So all of these things are vertical. We gotta go according to the order of operations. So multiplication first, addition last. And the only thing that is gonna change is the output, not the input. So the input is still 10. Multiply the 20 by 2, giving us 40, and add 7. 47. Good. J. Now, this is new stuff. This is a new example. So please, uh, I know you may be losing um, um, attention, but please pay attention to this example. This example is super duper important. Remember how when we do things horizontally, which means changes that are happening to the input, not the output, happen in backward or reversed order or reversed as we expect. Like multiplying by 2 in the input means a shrink. You know, you don't expect a shrink by a half. You expect initially, when before we learn about this, we expect a stretch. So this 2 is thought of as backward. And when we add a number, we're actually going to the left inside. So this means going to the right and shrinking. But the order is reversed. So remember how there is PEMDAS? You know, parentheses, exponents, multiplication and division, addition and subtraction. Well, that's true in the vertical. When we're talking about functions, in the vertical case, that's true. But in the horizontal scenario, it's exactly backwards. AS, addition, subtraction first, MD, multiplication, division next, exponents, and parentheses last. Isn't that weird? It's totally backward. So our intuition, because we are trained on PEMDAS, says multiply by the way, this is going to affect the input, not the output. So the output is still going to be 20 because we're still working on this original problem. The input is going to change. So let's walk through this carefully. We're going to shift to the right first. So we're going to shift from 10 to 14. So we're going to go from 10 to 14 because we're going to go to the right by 4 units. And then we're going to shrink that by a factor of 1/2. And that's going to give us 7. If you do it the other way, we're going to get the wrong answer because you're going to say, oh, it's the same. No. If you do 10 multiplied by, or even if you shrink it, it doesn't matter. You're going to get the wrong answer. And I can see giving a multiple choice problem where I'm going to give all the wrong answers, and you have to figure out which one is not the wrong answer. So, you know, if you do multiply by 2, you get 20 minus 4, you get 16. That's the wrong answer. Or somebody could say, wait a minute, that's actually a shrink. So shrink the 10 by 1/2, that gives us 5, and then add 4 because we're moving to the right, that gives us 9, not 7. 7 is the answer here. Why? Because not only the transformations are backwards as we may expect. By that, what I mean is that subtracting actually shifts to the right and multiplying by 2 actually shrinks by 1/2. But the order in which we perform those is also reversed. Instead of multiplying first and shifting, we have to shift first. So that means shifting to the right by 4, giving us 14, and then shrinking by 2, or by 1/2 rather, giving us 7. Very, very important example. Very crucial example. If you have the numbers outside, just use regular PEMDAS. But if the transformations happen inside, then don't use PEMDAS, use ASMDIP, whatever.
Are you there? Are you there? Are you there? Are you there?
Somebody called and then I had to pick up the phone. And anyway, I was talking about the backward PEMDAS, and I was trying to pronounce this, but of course I was just goofing around. It's just the backwards of PEMDAS, of regular. operations. Um, there was one other thing. Oh, yes. If when you take trigonometry and other things like that, people don't seem to like this too much. There's a second way of looking at that instead. I just want to make a note of that. Um, they factor out whatever the coefficient is, even if it's not factorable, they still force the factoring. So to quantity x minus 2 in this case, but whatever the coefficient of x is, they force a factor. And then the reason why they do that is because then they want to preserve the PEMDAS. Then you're okay. Then you can do this two first. See, it's not even preserved because that's a shrink, that's a stretch after the shrink. But if we do this properly, um, we would have to shift first. I mean, according to PEMDAS, and then do the shrink. However, we still do it backwards. I just wanted to mention that in trigonometry, it is common to factor the coefficient, and this is called a phase shift. Instead of a regular shift, it is called a phase shift. So I just wanted to throw that in there. We're not going to talk about phase shift. We're not going to talk about that in this class. That is more of a trigonometry topic. But in case you eventually encounter it, it doesn't contradict any of what we did. It is just a different way of coming up with a shift by first factoring out the coefficient. And we're gonna, this is a hard um, topic in my opinion, because it is full of new things, you know, adding, subtracting, adding outside, adding inside, looking at the graphs. There is a lot of stuff going on in this section. So this is what I would call a heavy section. It is fun though, it is good. Once you start mastering it, it feels really good. You have a better understanding of what the functions or the graphs of the functions uh, after going over this and going over many examples. All right, we're gonna stop the video here.